Okay. Okay. Today we want to continue our research in gradient neural networks. We will go shortly in the history of our research, and then we'll continue with new models. Here is Simulink implementation of GNN model for solving linear matrix equation. We remember conditions about consistency of linear matrix equation, AX B equals D. We remember this GNN model. I remember a general solution, which is based on initial state. Remember error matrix. And after linear matrix equation, we considered model for matrix inversion. Here are activation functions. It was our tutorial. Part about solving nonlinear equations. And then we investigated the model for solving matrix inverse. So we had switch from general linear matrix equation, AXB equals D, with respect to X, to simpler equation AX equals I. Then error function, of course, is defined in this way, AV of t minus E. Goal is to minimize Frobenius norm of this error function. And because of that, we use the gradient neural dynamic. This dynamic evolution goes during time in direction of negative gradient. A transpose, AV of t minus I is our gradient, minus gamma, because we want a negative gradient. And this here, calligraphic F denotes nonlinear activation function. We spoke that gamma should be as large as possible. And during our tutorial, we made numerical experiments with different values of parameter gamma and different time intervals. Here is corresponding result about convergence. General solution obtained using GNN model for solving such matrix equation is given in the form tilde V of 0 equals A dagger plus V of 0 minus A dagger A V of 0. Do you remember why do we use V of 0 here in index? We used V of 0 here to denote final result, because we wanted to mention that V of 0 is important in deriving final result. If we change V of 0, initial state, then we will obtain new solution. And in this way, we will be able to generate all least square solution. Solution obtained by zero initial state, V of 0 equals 0, will give only Moore-Penrose inverse. And the Moore-Penrose inverse solution represents minimum norm solution between least square solutions. Such solution is also called minimum norm less square solution, or many times we will say best approximate solution. What can we conclude according to this general solution? If V of 0 is arbitrary and the matrix A is non-singular, then here if we multiply from left by A or multiply from right by A, we will obtain identity matrix here. Why? Because A dagger will be A inverse of A. We assumed invertibility. It will be identity matrix. Here, A V of 0 minus A dagger A, which is A V of 0. It will be cancelled as always. And we will have in right-hand side identity matrix. Similar situation will appear if we multiply from right. Conclusion is V of 0 can be arbitrary, but in a case if A is non-singular, result will be matrix inverse. Another situation is when matrix A is left invertible. Or if it is full column, then we can again use arbitrary V of 0. If A dagger is identity matrix, we will have similar situation. And if we have rank deficient case, then A dagger will not be identity matrix. And the strong requirement is that initial state must be zero matrix. Then we will have again Moore-Penrose inverse. Now it is time to develop a GNN model for computing Moore-Penrose inverse. We know that Moore-Penrose inverse is defined using 4 matrix equations. Equation 1, AXA equals A. Equation 2, XAX equals X. AX star or transpose in real case. Here we will work in real case equals AX, and 4 XA transpose equals XA. Typically, in literature, such matrix equations were not, better to say, had not been used. Several years later, with my co-author, Marko Petković, we decided to use matrix equation 1 in defining Moore-Penrose inverse. It was for the first time in 2019, I think. Before that, in literature, for the development of GIAN model, matrix equations which were used are A transpose A, X equals to A transpose, or XA A transpose equals to A transpose. It is property of Moore-Penrose inverse, and in literature, Moore-Penrose inverse is computed using this property equation, not basic 4 equations established for definition of Moore-Penrose inverse. And our model presented here, which will later during tutorials will investigate in details, will be based on such matrix equation, A transpose A dagger. Okay. A transpose A dagger equals to A transpose. This formula should be used if matrix A transpose A is invertible. ZNN model requires invertibility of mass matrix. Mass matrix here will be A transpose A. If this matrix is not invertible, we will try with dual case, A transpose A Moore-Penrose, A transpose equals to A transpose. This model is preferable if matrix A transpose is invertible. What will be result then? Moore-Penrose will be A transpose and inverse of A transpose, which is well-known representation in case if A transpose is invertible, or in case if a matrix is of full row rank, which means rank of this matrix is equal to number of rows. Opposite case, dual case, is A transpose A dagger equals A transpose is applicable if A transpose A is invertible, or if matrix is of full column rank. It means that all columns are linearly independent, but number of rows can be bigger than number of columns, and we cannot expect linear independency of all rows in this case. Here, we choose this case. Dual case is can be developed in analogy, and we will skip this. Question is, what if both A transpose A and A transpose are not invertible? Will we have solution in that case? Moore-Penrose always exists, we know this. And we should find one method how to compute Moore-Penrose inverse. And we spoke several times about this approach. I will frequently say about this trick. So, yes, Tikhonov regularization. If we have no invertibility of A transpose A, nor invertibility of A transpose, we will use Tikhonov regularization approach. We will add one small regularization parameter lambda, multiply identity matrix with this parameter, and obtain regularity. Lambda should be small value, of course. We will analyze model based on matrix equation A transpose A dagger equals A transpose. Or minus A transpose equals 0. So error function will be, can you help me? Error function will be A transpose A V of t minus A transpose. Replace matrix which we want to approximate by V of t. T is time, so approximation will go across time and make approximations. Because of that, we call such neural networks continuous time, and called such networks recurrent because we allow cycles in communications between blocks included in model. This cycling was here. One possibility is to go to exit. Another possibility is to go back and prepare computation for next time instant. Goal function is defined as error function is error function. We want to force error function to 0. How to force error function to 0? Using nonlinear gradient descent methods. How to apply nonlinear gradient descent method? Minimize Frobenius norm. Practical for application is 1/2 of square of Frobenius norm. Frobenius square. And then define gradient. Not derivative with partial derivative. It is derivative of scalar with respect to matrix. Derivative of scalar with respect to matrix, because our goal function is one scalar value. And we want to force this scalar value to 0. But this scalar value is function of matrix, and we use derivative with respect to this matrix. It is half n square A transpose A transpose A transpose A V of t minus A transpose. From right, we have no factors, otherwise these factors will appear here. Of course, it is the same as A transpose A. Now we use standard, and always used GNN dynamics in form time derivative of V is equal to minus gamma. Here can be nonlinear activation. Calligraphic F can be without nonlinear activation. And our dynamical evolution, our dynamical system, our dynamics will be time derivative of t equals to minus gamma A transpose A transpose A V of P minus A transpose. It is model which we want to solve. And because of that we aim to solve such dynamical system, such system of ordinary differential equations. We developed this Simulink model. We will analyze this Simulink model shortly. First, I must say that rules in defining this Simulink are the same as rules for defining previous Simulink models. Input is matrix A. It should be defined. We can define my matrix A here directly. We will see this in new tutorial. Double click, open this block and put a constant value as we want. Or later A can be defined from command line. A prime is A transpose, and we will go step by step during model. Matrix multiply. We have two inputs, one output. Link which is first from top to down will be first in multiplication. So first we will have A transpose and then A and go future. Future left and right. Left goes in this part, right goes in this part. Because we have A transpose A two times, we need these two times. Analyze first left part. Here is A transpose A transpose A times V of t. V of t is output of ODE solver. We spoke that ODE solver is main part of this implementation. All is in hands of OED solver. If solver can work properly, if you obtain appropriate output from solver, all will go simply. No problem to multiply matrices, no problem to make addition, subtraction of matrix. Problem is to solve this system. Output is V of t. And we spoke that this solver requires initial state. This initial state is used in initial time when we had no previous results from right-hand side. This value, V of 0, is used in initial time instant. And here we have product A transpose A, V of t. And continue. Here is plus minus block. Plus is for A transpose A, V of t. Minus is for A transpose. Go here. And above is A transpose A. So the matrix multiplication is defined in this way. And finally, we need gamma and multiply gamma by -1. So here is minus gamma Another possibility was to remove -1 and put in the gain parameter, double click, put there minus gamma, for example, or minus something. Typically, it is not standard to define negative gain parameters. Because of that, I choose to use positive gamma as it is normal situation and multiply by -1. It is minus gamma A transpose A and so on. It is V dot in our model. But MATLAB this part allows LaTeX commands, but .v will not work. Because of that, I used v prime, which is not completely correct, because v prime can mean transpose. It is not transpose. It means v dot. And here is time for ODE solver to solve this system of ordinary differential equations. Output is v of t. And then we go in next time instant from beginning. And in this way, from one time instant to another time instant until when will we stop? When time interval is finished. We can choose time interval in which we evaluate this model. And when time interval is finished, we will go to end. Here, I choose and to put here one display block to see result of computing. It should be, what can we expect here? Here, Moore-Penrose inverse. Here we can expect Moore-Penrose inverse. Can compute Moore-Penrose inverse in MATLAB in another software and compare our result. Here is time scope. We will obtain graphs of all elements in V of t. In many of my presentations, I had question, Professor, we obtained here many graphs, but there is only one output, V of t. Yes, only one output, but this output is matrix. And this time scope will display graphs of all elements in matrix V of t. We will say time scope will present element-wise graphs of V of t. What can we choose another? We can use block to workspace, and then this block to workspace will save all computed results, and later we can use these results for our analysis. Then it is good to use Frobenius norm here. Cut here this stream, put Frobenius norm, and analyze Frobenius norm. It is good to trace element-wise trajectories obtained here, but it is also good to trace behavior of Frobenius norm, because our goal function is Frobenius norm. Conclusion is we computed Moore-Penrose inverse using error function. This error function is continuous time error function. We want to force error function to 0. And because of that, we choose error function Frobenius norm of this error function and minimize Frobenius norm. Frobenius norm, and finally, all other norms have 0 when have minimum 0. And this 0 value is obtained only when error function is 0 matrix. Yes, again, I will mention that we did in previous model, it is a standard model published in literature and can be found in arbitrary book about neural dynamics, about dynamical systems for computing Moore-Penrose inverse. Such 4 equations were not used in this standard model. And with my colleague, Marko Petkovic, we decided to use matrix equation 1 to define and compute Moore-Penrose inverse. Result published in Neural Processing Letters 2018. What will we have in this case? I must remove this. Better is to save for later comparison, but I must remove. What will be error function then? So, do you want to write? Okay, quickly. We have no time. We have much more models to explain. Error function will be -a, of course. Error matrix. It is error. A goal function is half of square of Frobenius norm of this error function. In save space. Okay, thank you. Yes, what will be derivative of this goal function with respect to v? Derivative by, okay, will be, what is in front will be A transpose will we have A transpose from right? Will have. And then we can use GNN dynamics and obtain this right here and obtain development of this GNN dynamics. V dot. They will not see this dot from this position. Gamma. Here is gamma. Thank you. Yes, it is correct. It is correct. Looks not the same as here, but this model is correct. Another model is correct. Why both models are correct? Because here we used error function AVA minus A. It was equivalent with the error matrix used here, A minus A V of T A. But I intentionally wanted to develop a GNN model for equivalent error function. Both models are equivalent. Finally, from this model, we can immediately switch to model presented in this table. Here we will use gamma and we will use opposite. There is corollary 3 aimed to result of convergence. What can we expect about convergence? As usual for GNN models, we can expect global convergence. It is typical for GNN models. When we want to say that convergence is global, we will say V of 0 equals V0. V0 means V0 is arbitrary initial state matrix. If you have problems with matrix, with convergence according to matrix which you choose, best choice is to use zero initial state. Sometimes zero initial state can give result if another arbitrary case will not give result. We can expect exponential convergence. Typical convergence for ZZ models is exponential. And we can expect such result according to well-known result presented for AXB equals D. Our case AXA equals A is particular case of this model, and we will obtain such general solution. General conclusion is given in 2. Set of all solutions obtained by arbitrary initial state matrix is set of inner inverses. Of course, why it is logical to expect? Because we develop model according to matrix equation 1. It is equation which defines inner inverses. Which solution we can expect if V of 0 is equal to 0? If initial state matrix V of 0 is equal to 0, of course, 0, 0, we can expect Murphy-Penrose inverse. In arbitrary case, if we multiply solution, theoretical solution V tilde V by A from left and by A from right, we will obtain A dagger A, which is A V0 A minus A V0 A. And general solution is defines inner inverses. But in particular case, V of 0, we will obtain Murphy-Penrose inverse. Finally, Murphy-Penrose inverse is included in set of inner inverses. Most popular inner inverse is is more pronounced inverse. Do you know some also very popular inner inverses? Which inner inverse is also very, very popular? Is it Drazen inverse? No. Group inverse is very popular. Drazen not. About tutorial and talk of my colleague Safik, which spoke about instability. I tried Simulink model for matrix inverse on Hilbert matrix. And first generated 4 times 4 Hilbert matrix. Result came immediately. And I quickly sent a message on WhatsApp. GNN works without problems. But in 10 times 10 matrix, we will see during our tutorials such situation. If not, please remember me. And for 10 times 10 matrix, GNN works and cannot reduce norm of error function. Cannot reduce norm of AX minus C. And progress mentioned in MATLAB was 0. Stayed in beginning, and it was cannot solve this matrix inverse for matrix Hilbert 10 times 10. Then I asked Mathematica, package Mathematica. We will see Mathematica also. Mathematica works excellent. 4 times 4. 10 times 10. 20 times 20. 50 times 50. Why Mathematica works perfectly? Symbolically. Exact computation. And Mathematica don't care about bad or ill or well conditioned.
But exactly when you compute, and
then I use the numerical value, numerical transformation of matrix of Hilbert for 4 times 4 finished. For 10 times 10, Mathematica was clever and said, it seems here is a bad condition, ill-conditioned matrix, and don't believe to results a lot, and gave some result which is not inverse, I think we will have another solution. I didn't try so far. My plan is to try increase numerical accuracy from 6 digits to 100 digits. I suppose that Mathematica will work again. We'll try this during our tutorials. It is Simulink implementation of A equals to A. Here is our model, which we want to implement. Where is beginning? A. Matrix multiply. For the first time, we have a matrix multiply with 3 inputs. First is A, second V, and then again A, V, A. Minus for AVA, plus for A, and here is A minus AV of the A, go to MATLAB function which defines Frobenius norm. And here we trace Frobenius norm. You can observe here very, very fine result obtained. In future, we can choose between pure linear model with linear activation, better to say model without activation than model with linear activation. Power sigmoid and smooth power sigmoid. In our testing, so far we used such two nonlinear activation functions. Here is one switch, another switch. Result is nonlinear activation function applied to error function. And then we need to multiply this error function, non-linearly activated, by A transpose from left and from right, obtained here, multiplied by gamma. Double click, we can change gamma, bigger gamma, better result. And it's time for ODE solver again. In ODE solver, you can choose solver ODE 15S, ODE 4523, and so on. And after that, here we have two choices. One choice is to go back in cycle, new time instant. And from one time instant to another, we go from initial time t equals 0 to time interval which we define in a Simulink model. In final time, when time interval is finished, we can present this result using display block, can use scope block to print element-wise trajectories, can use two workspace block to remember V of t, or remember Frobenius norm of V of t. Oh, here is. Because there is enough material for one tutorial, but when we have time for tutorial, we will see this behavior of these models. Now it's time to present some more models. We had such evolution in development of GNN design. Natural evolution is first step, compute inverse, which requires I'm thinking put here x or V of t. If I put x, it will be matrix equation which we want to solve. But I put here E of t. If I don't put E of t, I will put equation. Of course, there is corresponding E of t. A V of t minus E. Second, it was first result 1993. Chinese researcher Wang developed first GNN model for computing matrix inverse. We can say that this model is not so old. Better is to say this model is young, recently developed. First ZNN model is developed in 2001 year. Then next step is more Penrose. It is typical evolution in mathematical research. It is not only in only here in GNN design. It is typical for all in all fields of mathematical research. Here, equation considered is A transpose or dual case. Oh, no. Depends on invertibility. If matrix is left-right inverted, we will choose one of these two models. If not, if matrix is not left invertible, not right invertible, which means a rank deficient case, it is a rank deficient case, then we will use Tikhonov regularization. I must mention here GNN model based on matrix equation 1. I must say that in mathematical research, when people investigate Moore-Penrose, still is more popular to investigate A transpose AX equals to A transpose that than this one. Why, next question, why we choose AXA equals A? Why we didn't choose XAX equals X? But this model is complicated. Result will be the same, I think. We will generate outer inverse. And then we decided to investigate outer inverses. What will be with the Simulink modeling if we want to attack matrix equation 2, XAX equals A? It was not investigated previously. Finally, we want what is this which I defined? XAX equals X, and we have defined range, image, we can say image, and null space. It is a class of outer inverses with predefined range and or null space. We can ask only range, only null space. If we ask both range and null space, then we will obtain one unique outer inverse with such properties. So next goal in our GNN research was investigate outer inverses with predefined range, null space, and so on. And here is theoretical basement which we used in our research. Outer, it is representation of, do you know what is this? Outer inverses with rank equal S, given in the following way. GAF is invertible of rank S. If not, here we can put arbitrary one inverse. We will have this situation later. We have 1 week more, and will be situations. Outer inverses of ranks from 0 to R. If we consider rank 0, what will be then? It is only zero matrix because, and finally, this case is, how to say, trivial case. We will not investigate them. Better is to say here from 1 to R. But zero matrix is one outer inverse. We cannot say not. 2, 4 inverses with rank S. VA dagger, V. V is matrix of appropriate dimensions. 2, 3 inverses. 1, 2 inverses are outer inverses with rank equal to rank of A. Full rank representation of Moore-Penrose inverse. Here we can put PQ instead of A, we will obtain opposite Q star, Q star minus 1, A, and then there will be opposite. Right inverse of Q times left inverse of P. Here is a full rank representation of group inverse of group inverse. QP is non-singular. Of course, our request is index equal 1, and the rank of A must be equal to rank of A squared. And here, there is our first model, which we developed aimed to find outer inverses. It is typical evolution. It is my recommendation for your research in future. Always research in generalized inverses theory goes from matrix inverse, then goes to Moore-Penrose inverse. Next step is Drazen inverse typically. Our first paper was aimed to Drazen inverse and not included here. Drazen inverse will be based on AK plus 1x equals to AK, or it is equal to AK AX. Identity matrix for inverse, A transpose for Moore-Penrose, A power K for Drazen inverse, and G for outer inverse. And you can trace this research in all fields aimed to generalized matrix inversion. And when you have result for arbitrary inverse, we can always go to outer inverses with prescribed range and null space. But there is one condition for consistency. If I want this condition, I must go to consistency condition for AX, B equals D. Or you believe that it is condition. Pedagogy will say not good to go a lot back in your presentation. Here is condition 12. A dagger B, D, sorry. equals D. So here corresponding condition will be, please help me. And then what then? This right-hand side here, right-hand side is sorry, here is condition. I wanted to verify and did non-pedagogical movement during presentation. Such condition must be satisfied. This condition is not because of drawbacks of GNN model. This condition is according to requirements of linear algebra. It means projector of GA orthogonal. It is orthogonal projector times G must be equal to G. Here can be arbitrary one inverse. Situation will be the same, which means it is equivalent to rank of GA equals rank of G. It is first rule. So it is good to choose matrix G such that rank of GA is equal to rank of G. Then if A is matrix real, for example, of dimensions m times n and rank R, G should be of opposite dimensions n times m and rank S, such that S is greater than 0. Greater, we don't want to investigate 0 matrix as outer inverse, and less than or equal to R. R is rank of A. What will be if rank of G is equal to rank of A equal to R? Then outer inverses will be reflexive inner inverses, 1, 2 inverses will satisfy equation 1 and 2. In any case, I will continue later, so 5 minutes less or more is not important. Will be the same, result will be the same. So it's time to develop a model for J AX equals J. We want to solve this equation. I will clean table, and if you are willing, someone can help me. You cannot say, professor didn't want to clean table. I clean table, and probably someone can do this. Can you do this? Do you want? Thank you. Please try. GAX equal G. It is our equation which we want to solve. E of t is equal to Yes, inappropriate. One part of table and another part. E of t is equal to. Can you see? I will write once more. I write here GAX. Error function is V of t minus G. Goal function is, they work. Fight. Shaman works also. Shaman can do this. I want another to do this. V of t. Frobenius norm square. Then we need derivative of goal function. It is kind of gradient. And later we will use gradient descent method. But I must say it is specific gradient descent method. Why specific? Because step size is as bigger as possible, as longer as possible. Because of GA in front of V of t, we will have GA transpose. GA transpose. GA. Transpose, but here is open. Transpose, and then this one. Right, nothing. Here is nothing identity matrix. From right, we will have no. GA V of t. If we have here matrix C, will be C transpose, but we have no.
So identity into?
We can say identity is here. Nothing is right from V of t. And then GNN design.
Yep.
Minus gradient, step size, and then gradient. Here is partial because it is matrix and in this way we will obtain time derivative of t equals gamma no. Non-linear activation, of course, possible. Possible to write without calligraphy F, which means we will have no non-linear activation, but if we put calligraphy F, it will mean use non-linear activation. It is good. It is model presented here. What is with the initial state? Arbitrary, can be arbitrary. Typically, it is good to mention what is initial state. Thank you very much. Thank you. Now it's time to see what is general solution. General solution is given in the following form, in form 28. It is again in accordance with the general model for AXB minus D. it is model generally. And if we solve this model, all will go automatically. We will have all matrix inverses. But we will have no Sylvester matrix equation. It requires independent research. It is general solution. Which kind of inverse we can expect if v of 0 is 0? Is there 0 initial state? Expert is mathematical analysis. We can expect result 0 matrix, 0 down, I will put, v of 0 is 0, is GA dagger G. It was a representation of these two four inverses. What is conclusion? We wanted outer inverse and obtained 2 4 inverses. Of course, 2 inverses are included in this class. Yeah, but it is part of outer inverses, but our final goal was how to obtain outer inverses. Is it outer inverse? Can we verify? GA dagger G, then I will make one. It A, again, GA dagger G. What we have? GA dagger, GA dagger. Equation 2 for Moore-Penrose inverse. XAX equal to X. Equation 2 is satisfied. Is equation 4 satisfied? Then A, of course. Why this equation is satisfied? Satisfied according to property, according to equation 4 of Moore-Penrose inverse, but it is if we apply property 4 for Moore-Penrose inverse in case of matrix GA, we will have that it is equal to GA dagger GA. So G A dagger Moore-Penrose G belongs to rank as the same rank as rank of matrix G. Why ranks are the same? Why rank of GA dagger G is equal to rank of G? We ask rank of G equals rank of GA. It was our assumption. And finally, rank of Moore-Penrose of GA is equal to rank of GA. And product must have the same result. We can define two, four. What is range of GA dagger G? Experts in mathematical analysis. Here, more mathematical analysis than linear algebra. it is, do you know well-known property? Image of AB is equal to R of A if and only if rank of AB is equal to rank of A. We have rank of GA, dagger G is equal to rank of GA. So image of GA dagger G is equal to image of GA dagger. Image of GA dagger is image of GA transpose, because range of Moore-Penrose is range of conjugate transpose. Or it is null space of GA transpose. What is null space? Property, rank of AB, rank will be later. Null space of AB is equal to of B. One side is always satisfied. Subset here is always satisfied. Zeros here imply zeros in AB. If and only if, again, rank of AB equals rank of B. Rank of G is equal to rank of G. And here is N of G. We found range and null space. But it is 2 inverse. We wanted 2 inverses, and we'll continue later research how to find only outer inverses, class of outer inverses. Okay, we can formally stop first. It's time, yeah, I think, stop.
Thank you very much, Professor Predrag, for your wonderful talk. Now, if you have any questions, audience, please go ahead.
Since inner and outer inverse is not unique, so for any different initial value, we can get different answer for computing.
You asked question about initial state matrix. Initial state matrix will give
different
values of initial state matrix will give different results according to this rule. Yeah. Is a matrix equation for this matrix tilde V. Is this matrix equation GAX equal G satisfied? Multiply from left by GA. We will obtain GA dagger G, which is equal to G plus GA V0 minus GA V0. Cancelled as always. Of arbitrary. Which is equal to G, because G belongs to range of GA. It is projector. It requires a projector on orthogonal projector on the image of GA. And rank of GA is equal to rank because of our assumption that rank of G is equal to rank of GA. Results are different, but always satisfy this matrix equation. Finally, solution of this matrix equation is not unique. And if we change V0, we will obtain different solutions.
Thanks.
You have any question?
Hmm.
Okay, if no question, please give big thanks to.
Thank you. Thank you. Shortly. Make tea break or not tea
No.
break? Don't want tea break.
Oh.
Water break. Short water break. Okay, water break. Here is Simulink implementation. Details are the same. Input is given in matrices G and A.
Can speak better, so they have stopped light.
Huh?
Your next class.
Next, we continue. We will
We have
continue.
stopped,
Stop recording.
yes.
Then short break in any case, huh?
Ratikanta will speak now.
No,
You?
I think.
No.
Please verify. I think I will speak and then Artikant. I think. Verify.
Timetable?
What is timetable? Do you have timetable? Here is corresponding GNN model aimed to implementation of GNN design presented in this way. Gamma is here. Again, we go cross-model step by step, multiply G and A, then use block for matrix transposition, GA transpose. Down, we will prepare GA V transpose, then plus minus will give GA V transpose minus G, multiply both of them. Then we need minus gamma obtained as positive gamma multiplied by constant -1. And here is completed right-hand side of our GNN design. And we can assume that this stream is just a time derivative of V of t. According to our model, we can assume here is V dot of t. From V dot of t, we need V of t. Our goal is to find V of t. V of t is approximation of 2-4 inverse. Then we need solver, ODE solver here, and output will be V of t. And go back to recurrent neural networks. Because of such cycles, our neural network is a recurrent neural network. In another time instant, and from one time instant to another, we will achieve end of time interval. After the end of time interval, we will print elements of matrix V of t. We will use to workspace block with possibility called SIMOUT1. Later we can plot this data included in SIMOUT1 analyze, not only plot, analyze statistically in another ways. And we can put here timescope block with aim to plot all elements of V of t. So here we can expect n times m plots in one graph, because the resulting matrix tilde V of 0 will have n times n entries. Here is our attempt how to define GNN model for computing outer inverses, not 2-4 inverses, and 2-3 inverses in dual case. Dual case will be XAG equals to G. What is assumption about matrix G? Rank of G must be. Otherwise it will not work. Then we will obtain 2-3 inverses. And now is GNN model to obtain 2 inverses exactly. We found this model, say, intentionally. We had no idea occasionally. We found this model occasionally. How we did it? In that time, we were not expert in GNN, and we thought that this term, GA transpose, is step size, and simply deleted this term GA transpose with the intention, with not clear vision what will be in future. Our idea was to simplify original model. Only reduce step size, remove GA transpose, and obtain faster GNN model for computing the same class of outer inverses. But class was not the same. Class was just what we expected, outer inverses. So here we will consider simplification of this GNN model aimed to computing GAX equal to G. In this way, remove GA transpose. But it is not a GNN model. This model is not a GNN. And what can we expect in this case? How we started to investigate this model, verified frequent divergence. Opposite to previous experience with the GNN model, experience about global convergence with arbitrary initial state matrix V of 0. Here we are working with model 29. We realized divergence many times. Why we realized divergence? Here is. Here is, I will go to Simulink implementation later. I will explain why we obtained divergence in many cases. Later, we verified this theorem, theorem 3, which says that spectrum of GA in real matrix case must be non-negative. If we consider complex matrix here, then we must ask real parts of eigenvalues to be non-negative. But I combined here is real matrix case. So only lambda J is enough. In complex matrix case, we can consider here real part. And if this condition is not satisfied, we will obtain divergence. Modified GNN design, we call this design later RNN-ATS2, RNN-ATS2, because it is not GNN more, but it is RNN, it is recurrent neural network, it is still continuous time recurrent neural networks. So lambda J eigenvalues must be non-negative. For each possible eigenvalue. And later we found theoretical solutions of our RNN model. It required a lot of learning in ordinary differential equation theory, read books about linear algebra, differentiation, and the general solution of a modified GNN model without GA transpose is given in the following way. We don't need the GNN model practically. We ask Mathematica to symbolically solve involved GNN model. Mathematica gave always this expression during in all time instance. If we use zero initial state, we will lose first part and result in zero initial state matrix case will be given in the form 32. And we asked after that limiting value, what will be if time continues to infinity, result will be outer inverse with prescribed range and null space. But range and null space here is the same, defined by the same matrix G. GG. Later we investigate why GG. Give me BC inverse to compute BC inverse. And compute it later, recently. I hope in the end of next week we will go to outer inverse. BC inverse is here. It requires two matrix equations. If you remember about BC inverses, Drazen introduced BC inverses in linear algebra and its applications journal in 2012. But we must solve both of these equations. It required a new technique how to solve system of matrix equations. Then we must use composite error functions given as one block E1 of t for first, E2, we will have two error functions, make one block error function. After that, Shaban knows this, vectorizations, Kronecker product, and obtain one long vector. And if we implement such models which can solve AX B equals B and CAX equals C, we will obtain BC inverse. If we use only one matrix and one matrix equation, GAX equals G, we will obtain outer inverse with range and null space defined by the same matrix. If we use the same matrix, we will have two dual cases. Which case we will use? What we can recommend? It depends on dimensions of A and G. If AG is of dimensions M times M. A is of dimensions M times N. G. So AG is, if M is smaller than N, we will use then AG. A is of dimensions N times N, and if N is smaller than M, we will use this model. Why? Because dimensions of matrices will be smaller. We can expect faster computation. Again. Here is proof requires. I will skip this proof. For example, if some of you is interested and consider this. It is a general solution of simplified GNN model. It is not GNN model more without GA transpose. And later we need transformations. I use one useful property. G is equal to GAX. Professor Wei finished this proof. Yes, we stayed here several months. How to prove that limit of this is outer inverse. But if we put here GA, outer inverse, R of G, N of G, here we will have simply, here is, determines how to explain. Here is solution exponent of G, gamma GA tau from 0 to T. It will give the following result. Use that limit of exponent of minus gamma GA transpose is 0 and obtained outer inverse. It was published in Applied Mathematics and Computation. A very good result, new result. Finally, we obtained rule what will be with arbitrary time instant and found convergence result. Reviewers were, how to say, bad, in this case, editors in many journals, because we published a relatively big number of papers about GNN, about outer inverse. But finally, in applied mathematics and computation, understood this result, and it is published recently, 2021, I think. Here is an example. After lunch, we will have a tutorial. Or afternoon, we will have tutorial, and we will see such behavior. We considered matrix A and G defined as minus A transpose. When we make testing of our RNN model, modified GNN model, we frequently obtained divergence, such situations. When we wanted to analyze, we could not find worked. Finally, we decided to use G equals to minus 8 transpose. Surely, then GA will have negative eigenvalues. Result is catastrophic. There is how to solve this problem. The solution, not perfect. We must have fulfilled condition lambda J greater than or equal to 0 for all eigenvalues. If one or more of eigenvalues is negative, we will obtain weak divergence. Solution is to use matrix. Instead of G, use matrix G0. I think I will try without reading. Yes, this matrix, then it will work. Because range of G0 is the same as range of G, null space of G0 is null space of G, and lambda yacht of lambda J of G0 is always greater than or equal to 0. And it will always work. Will, but slow. Numerical experience say that such GNN model is much slower because we replaced G by G times GA, G transpose, G. Numbers in this matrix increase rapidly. And how to say, progress during time is much slower in this case. Here is result obtained by the same modified GNN model, but in case when G is replaced by G0. What is drawback? After much longer time, we will try this experience during our tutorial. There is one job for Shaman. Should be prepared for afternoon. I will present GNN model in this form. Your job will be to transform this true GNN model to RNN model 29. You must delete some blocks from GNN model and obtain another one. We will try to do this in afternoon. So it is a general rule how to trace results in generalized inverse theory in the results in general case applications in engineering. Why not? All starts from matrix inverse. That another step is pseudo inverse or Murpanow's inverse. Murpanow's inverse is based on A star. Inside this, algorithm goes with A star. Then Drazen goes with A power K with Rankine variant powers. And if we use arbitrary G, we will obtain outer inverse with a range and null space defined by G. If we use two equations, such two, we will obtain BC inverse. And always, if you have results, find the result for Murpanow's, always can generalize this. Here is result about Drazen inverse. Strangely, in the end of this presentation, but according to year of publication, you will see that this paper was first. Yes, it was my first paper in GNN theory, in RNN theory. All started, we have 3 minutes, I think. No, not 3 minutes. We have 30 minutes. 30 minutes. All started around 2012. 2 years of investigation, or 1 year and a half, and 1 year and a half in publication of this paper. In meantime, all was stopped. We investigated, but not sent for reviewing. Waited result in IEEE. We asked IEEE, TNN, LS, which had waited. If we published something more general in another journal, we will lose this. And waited 2 years after that, published quickly. This research was aimed to Drazen inverse. What were equations aimed to Drazen inverse. Equation 2. One K and 5 commutativity. This equation is used. This equation is used in computing Drazen inverse. Here is equation corresponding to equation 1K. I put here VD to mention that this model is aimed to computation of Drazen inverse. It is our matrix V. Can be V of t here, but I put VD. Frobenius norm square is goal function. And 37 gives true GNN model for computing Drazen inverse. Constant here represents K. Constant K here represents index of matrix. Can we use bigger values of index? Bigger arbitrary number equal to or bigger? Why we use bigger? We will use index exactly. But always rules for the Drazen inverse are valid for L greater than or equal to K. Here is just index. And in that time, we deleted this term A, K plus 1 transpose. We were beginners and decided to remove this and don't mind that we made new GNN model. It was a requirement. It means, is it complex case? Real case. If we consider complex matrix case, then we can ask here real parts of eigenvalues in real case. And I prepared here yesterday one, one appendix for people interested in DMP inverse. How to compute DMP inverse. And after that, you will be able to prepare GNN model for arbitrary inverse. I had no enough time. I started to work in evening after many lecturing. Here is model aimed to DMP inverse. It is a result from Applied Mathematics in Computation, 2020. I don't know why this paper is still with DOI number, no page numbers. I verified in Google still with DOI number. After five years, no page numbers. But the DOI number is here and works. Here is introduction, what we did, remove GA transpose. And there is, in 20 is parallel model for computing outer inverses. And we know that DMP is outer inverse. Range defined in this way, null space defined in another way. I forgot to say what is DMP. Can you help me? What is DMP inverse? Name says Razin and Murpen-Rose. D dagger. And it is outer with range equal to a power k, null space a power k, a dagger. Then here is we need to solve matrix kind of one matrix equation of the form GAX equal to G. We need such equation. R of a power k and of I power k a dagger, not the same. If situation is the same, we will put G here to be. That situation is not the same. But if we change something, will be the same. What if we consider works? It is true. Use one A from here. A dagger A will be A. We will obtain again. So G, if we use G equal to, here will be GA and here will be G and there will be GA. Later we obtain the solution. In this lemma, we obtain some properties of DMP inverse. It can be simply verified. For example, here replace DMP inverse of A by A trace in A dagger. A dagger A star is equal to. We use this property to define GNN model for Murpen-Rose. A dagger A star. A star. And immediately we will obtain A Razin A star. Simply verified conditions. Again, here, A Razin A Murpen-Rose, but A Razin A and A can change place. Here we will obtain A k plus 1 A Razin, which reduce to A k simply. And we, in the development of GNN model, we used equation 41, property 41. Sorry, I will be slightly slower than it was publication in 2020. We worked on this paper during my visiting in 2019. We will use here such transformation. Here is a power k can be represented in this way, and here is g. Here is g. And we need to solve equation GAX equal G. If we apply true GNN model, we will not obtain only DMP inverse. We will obtain class of two four inverses. But DMP will be inside this class. But if we apply modified GNN model, we will obtain DMP. Here is modified. What will be in true GNN model? What will have? What will be here in true GNN model? Here, it is simplified. Here I wanted to say that it is of the form GAX minus G, but it can be simplified to a power k. And if we consider it is a power k always, if we consider such error function and use Frobenius norm, then use derivative, what will be in front? Transpose will be, yes. If we ask true GNN model, here will be a k, a dagger transpose, yes, will be complicated, and we will not obtain only DMP inverse. Now I'm thinking probably we will obtain DMP in zero initial state. In zero initial state, it is one possibility. Apply true GNN model, zero initial state will give DMP. Another solution is to apply this simplified GNN model. It is not a GNN, RNN model. But there is one problem in applying RNN model. Oh, what was the requirement? Requirement was non-negative agent values. Non-negative agent values. But according to some conditions, we verified that in this example, agent values are not negative. Consider this example. We will, this example is performed in Mathematica. A input matrix. Compute successive ranks. Rank of A is 5 of A squared equals to A power 3 is 4. So index is equal to 2. DMP inverse is computed in Mathematica in the following way. How to compute DMP in Mathematica. DMP is defined as A Drazen, A dagger. It is equal to, do you know some representation, effective representation of Drazen inverse? How we can compute Drazen inverse? One effective representation of Drazen inverse. I want to compute Drazen inverse. Index is always there. I'm intentionally write A power K, A power K dagger. Arbitrary inner inverse can be here instead of Morpenrose, but best way, simplest way is to use Morpenrose. Here in our case, K is equal to 2. So it is sorry. I forgot here. A power K, A K, dagger, A K again. And it is A squared, A power 3. Simple job for Mathematica. Simple job for Mathematica. Pseudo inverse is name of this function in Mathematica for Morpenrose inverse. Not only PINV as in MATLAB. Mathematica uses long names. Exact computation will give result as here. Here is, like we will stop here. It requires 1 hour at least. It is interesting research. Here is Simulink implementation. Practically, we use the simplified GNN model with the G matrix in GAX equal G, defined as A power K, A dagger. A power K, A dagger in this function in MATLAB. Here is block for computing pseudo inverse. SVD, why SVD? SVD is inside Morpenrose. SVD, the composition is how to say, basement for computing Morpenrose inverse. We must multiply A by A, obtained A square. Finally, we have block for matrix powering. Multiply A square by inf of A. It is with GIAN. For simplicity, we denoted this matrix by G. And not only for simplicity, it was easier to trace behavior, what easier to transform general GAX model in this particular case. G, here is G equal, G with minus, A squared V of t with cyan plus, and here, not there, here. Now it should be started here, is A squared V of t minus G. Then we need minus gamma, obtained as product of gamma and minus 1. Here is V dot. Solver. Then go back in next time instant or go to exit. We will go in next time instant then again in next time instant. In one moment, time interval will be finished. And then we will go to exit. In our case, this exit contains display block. This display block shows values of V of t. What can we expect here? What? Sorry. DMP, DMP inverse. We can expect here, and here we can expect graphs, fine. Element-wise graphs of DMP. Can we compare only one? 0. Now we can compare exact solution with what is conclusion? The result here exact is 0.25, what we obtained. It means what we must do in such situation. Our solution presented in journal, okay, is not completely correct, but it is not important. What can we do to improve this? Activation function or increase gamma, or if we use the same gamma, we can increase time interval. Finally, we can increase time interval and also increase gamma. But if we increase gamma in big values, increase time interval, we will obtain a lot of unnecessary computations. We will obtain stable equilibria stage earlier, and we continue to work necessary. And in one moment here, we will obtain something approximately with 0.25 possible 24,9999 something, because numerical calculations around of errors give job, and we cannot obtain exact solution. Only exact computation and symbolic computation is applicable. So one tool is MATLAB, Simulink, for example, for computation in numerical linear algebra, time varying case or continuous time model. Another approach which I prefer is symbolic computation. Each researcher in numerical linear algebra should use this symbolic tool, symbolic an exact calculation. If you work on hand, you cannot obtain example bigger than 3 times 3. Here, the job to obtain such inverse is very easy. Here is A dot A, because dot in Mathematica is instead of star in MATLAB, A dot A, then pseudo inverse of matrix power A, comma 5 dot matrix power A, comma 3 pseudo inverse of A, and shift enter, and you will obtain this exact result. Or result can be in symbolic form. You can put here some symbols instead of only numbers, and I cannot use symbols in this example because we want to solve problem by gradient neural networks. Gradient neural networks can work with symbols, but in another examples, it was possible to use symbols. And when you obtain results with symbols, you can make some, how to say, assumptions. You can give some conclusions, theorems. You can later verify such theorems. To explain more, I think it will be later. We will use another approach. Again, does not work. Okay, I think it is time for questions. Who is chairman? Safik is chairman.
Okay. Time for questions. So if you have any questions, please continue.
No question.
I think already they have asked questions, several questions
Uh,
between lectures.
Okay.
Okay, if no, thanks,
Sir?
please give. Yeah, please, go ahead.
We have found the 2-4 inverse and like 2-3 inverse. Can we use all the 4 condition of Moore-Penrose inverse to define a model?
And but we need to develop tool how to solve system of matrix equations. We will consider this possibility. I shortly spoke that we will use several error functions. In case of Moore-Penrose inverse, we will use 4 error functions, and then make one composite block error function made of 4 blocks. And a right-hand side definition of these error functions will be also block matrix.
And in GNN model, our main goal function is minimization of Frobenius norm. So we can add plus alpha times one model plus beta times another.
What you want to say? Interesting. I didn't try it in a continuous time. In discrete time, I tried. We want to minimize. I will skip 1/2. It is a system of linear equations, of course, and minimized only this. Obtain least square solutions. Typically, zero initial state will give best approximate solution. You want here to put another part, one parameter, It is not Frobenius. It is two norm in a vector case. You think possible. I didn't found something similar. Something in this form. This model will go directly to Moore-Penrose inverse. This term, why it should go lead to Moore-Penrose inverse? Because we want to minimize norm also, not only residual error. We want to minimize norm, and it will be good model for computing Moore-Penrose inverse, probably later and other kinds. And it is very nice to investigate.
Okay, is there any other question? You take mic.
DMP,
In the similar way, can you compute MPD inverse?
of course. CMP inverse, why not? All kinds. All of these inverses are outer inverses with range and null space. Only is enough to find range and null space. Typically, researchers give many properties, many methods, but it is enough to find representation which gives outer inverse with range and null space, as it was here. MPD, of course, it is dual case of this one. Find properties of MPD and similar properties. Possible.
Continue.
Okay,
Finished?
I finished.
Yeah, any other
I
questions?
hope they didn't finish.
So if no questions, please give big thanks to.
Thank you.
Lunch? Lunch break, huh?
Oh, Shaman, we found new topic. AX minus B plus norm of this. I will show you one paper about this in discrete time case, with discrete iterations. Again, initial state is important. If we start earlier, we'll finish earlier.
3:34. So time is
3:30.
5 shift. Yeah.
3:30.
Yeah.
3:30, I think.
Yeah.
30 minutes to
Start.
5:30. We will finish earlier. No. Skip only. I don't know how to remove this. Read on the internet, but cannot find, and now disappear. They will start, I think, soon. Ready? It is our third tutorial. So far, I had one, Professor Savik one.
Okay, now we'll start our second session of third day. This is fourth day. Huh?
Fourth day.
Okay, go ahead.
Okay. In this tutorial, first I will make a connection with the previous tutorial of Professor Safik. I will show practically results of ill conditioning and well conditioning. First, I will use our GNN model for solving matrix inversion problem to show how ill-conditioned matrix can make difficulties in computation. We worked on this model. As you can see, this model is based on error function I minus AV of t. And according to that, this model multiplied by A transpose is aimed to find matrix inverse. What we need to define. First, it is not Simulink. Here is Simulink model. Of course, the same as in PDF file. Double click on A means here is A. So A must be defined in command line. What we need to define more? Gamma 10 power 17 is too big for beginning. 10 power 6, for example. It is workspace. Here will be stored values of matrix V of t during time, and later we can explore this stream. Here is two workspace block aimed to Frobenius norm of residual matrix. What initial state in integrator is V0, which means that we must define V0 also. We need to define matrix A and initial state V0. Time interval is from 0 to 10 power minus 2. 10 power minus 2. We will define matrix A first as random integer matrix. Rand A command. Then we will use interval 1 to 10. It means that we need random numbers from interval, integer numbers from interval 1, 10. And matrix should be of order 3, 3. Here is randomly generated matrix with entries 9, 7, 9, and so on. Values are between 1 and 10. V0 equals 0. We will choose 0 initial state. Try with our GNN model. According to what is the time scope? According to this time scope, I made double click to time scope 1 to watch what is with what happened with the norm of residual matrix, and or we can can see very fast convergence of this norm to zero. Here you can see details, and then this here is zero, all continues to zero. So we find the matrix inverse without problems. In very short time, it was in very short time 0.01, 10 power minus 2. Slightly bigger matrix A, example 6 by 6. Again the same situation. Here you can see convergence. When I made zoom to this initial part of graph, we can see fast convergence of error of norm of error matrix to zero. Number of element-wise trajectories increased, of course. I will try 10 by 10. The same situation, slightly slower probably because of bigger dimensions, but solved without problems. Here we have a lot of element-wise trajectories. Now we want to try what will be with the Hilbert matrix. In previous tutorial, we spoke about Hilbert matrix as one example of very ill-conditioned matrix. Standard MATLAB function for generating Hilbert matrix was HILB of 4, for example. It is Hilbert matrix of order 4. Let us mention that Hilbert matrix is matrix with entries 1 above I plus J minus 1. In Mathematica, I can show these values exactly. Here is 4 by 4 Hilbert matrix. One plus 2 minus 1 here, these two, and so on. Hilbert matrix of 6 will be the same. We defined matrix A as Hilbert 4 times 4 matrix. Now we will try what will be result with this matrix. What does it mean? This result which we obtain. What can you say? Will we obtain, do we obtain convergence? No. What we need to do? Increase gamma, increase gamma. Gamma equal 10 power 6 was enough in previous case. Now, in this case, is not enough. Increase gamma. 10 power 9. Looks as not enough. Here is convergence to 1. Here is not 0. Try with a longer time interval from 0 to 0.1 and bigger gain parameter, 10 power 12. What is exact inverse? Mathematica knows what is exact inverse of Hilbert matrix of order 4. Here is H4 minus 1 is equal to 16 minus 120, 0, minus, and so on. We will see what is situation in our Simulink implementation. It looks very, very close to 16. Another one looks very close to minus 220. Finally, if we increase gamma more, not questionable is if we can obtain something better than in this case, because it is numerical calculation. We cannot expect exact result. Many computations during time solving system of differential equations around of errors. We can see what is last element. Mathematica will say $2,800. Looks with really great precision. We can achieve even better if we increase gamma. In that moment, I was very happy. GNN can solve Hilbert matrix inverse without problems. And then tried with Hilbert matrix 10 by 10. Now I will try with slightly smaller. 8 by 8, for example. 8 is here. Again, the same situation. Here value is 1.60 is far from this. Bigger gamma, but we always work with gamma, which is big. Can put bigger. Can put longer time interval. From 0 to 1. And try. Change very slowly. But take into account, no, it is, we need age 8 minus 1. I will see what is element of, first element of age 8 minus 1 inverse. I suppose still works. Oh, you can see the same as me. 64 is first element. What happened with our Simulink? Still 28, 27.9, 64 is far. 64 is far. What? Gamma 10 power 17. 17? 17. Consider a progress line. Here is one small progress line which trace our progress in time interval. Even not started. Still not started. Cannot start, cannot find something better. 0% still is 0%. Time is 2.3 times times 10 power minus 4 in initial state, almost in initial state. Solver cannot find the appropriate solution and continue. So it's time to stop this and say that GNN model cannot solve this problem. But it does not mean, oh, GNN is bad, I will not use GNN. Hilbert is bad for all methods, not only for GNN.
For that one, develop some algorithm so that it will work.
For some small dimensions.
For higher dimension, can we develop some new GNN model?
New GNN model. It is GNN model for matrix inverse.
But it is not working for Hilbert.
Not working for Hilbert.
Can we make general GNN will work for all?
For Hilbert will not work, I suppose. It's time to stop this, I think. 28, still the same, always the same. Simulink goes from one time interval, very tiny time interval, try to find something better. Time is almost the same. Slightly bigger. Stop. No solution. Again, it does not mean GNN is very bad. I will not work with the GNN. Now try with Mathematica. We will see Mathematica in more details soon. Now I will show Mathematica only in this particular problem. Later, after several days, we will see with more details Mathematica. First, I generated Hilbert matrix using programming in Mathematica for cycle 2 times, define elements, use return. Without return will not work. It is required in MATLAB also. Return in end, and then function will return value. But later discovered that Mathematica has Hilbert matrix function. We will use this Hilbert matrix function, inverse of Hilbert matrix of 4. Fast job. Of 8 times 8. 8 times 8. Simple job. 10 times 10. Fifty times 50. Simple job, no problem. What is problem? Observe beauty of Mathematica. Fantastic tool for mathematicians. Still inverse. Watch how big numbers are here. And all finished in part of second. Work mathematics and don't use Mathematica is really, how to say, it's a pity. Where is end of this? Here is end. I can use bigger and will be, who knows, will be end probably 100.
And then for the inverse of badly conditioned.
1,000, I think, there will be limit with very big dimensions. Now I use numerical value of Hilbert matrix. Slash 2 times and then n means use numerical value with the usual precision. Here I transformed Hilbert matrix 4 times 4 in a numerical value. what happened then? Without problems. Only dot in the end of each number, which means I worked numerically. This dot means I worked numerically and obtained fantastic precision. Only put dot means all another. The decimal digits are 0. And then tried with Hilbert 10 times 10 matrix. Eight times 8 first. Mathematica said result for inverse of badly conditioned matrix may contain significant numerical errors. It implies that we can expect numerical errors. Did something, but we cannot be sure. We will try to solve this in using exact computation without n to see what is first element. Here is 64. I'm not sure, we will see. 64, yes. Lux Mathematica did and gave correct result. Had problems with ill conditioning, but solved finally. Ten times 10. Hmm. 100 is exact value, and the numerical calculation gave only 2 times 99. It means precision in 2 decimal digits. This result is not so good. And if we increase dimensions, we will have more and more difficulties, and result will be, say, further and further from exact value. For example, 15, I'm afraid that 20 will not be visible. 15, what exact computation gives? Exact value here is 225. 225. Here is 153. Far result is definitely very far from exact results. We increase dimensions, and problem was bigger and bigger. Smaller dimensions was possible to solve, but bigger dimensions after 10 were impossible to be solved. So one possibility to solve ill conditions is to use arbitrary precision arithmetic. Arbitrary precision arithmetic is part of symbolic computation. Another possibility to solve this problem is to use arbitrary arithmetic with arbitrary precision, not only exact arithmetic. Here, using function n with 100 decimal digits precision, I will try to find inverse of h of 8. H is Hilbert matrix. Looks good. Of 10. We can try. Here is inverse of Hilbert matrix. Then we will multiply A and X and see if the result is good. Inverse of Hilbert matrix. 20 with 15 decimal digits. And this far, I cannot use slider. What is X dot? Dot is matrix multiplication. Identity matrix. 1, it is times minus 36, which is very good approximation of 0. Minus 31, 0 practically. And it looks as a diagonal matrix, identity matrix. So arithmetic with 50 decimal digits precision is able to solve ill conditions of Hilbert matrix. Of course, exact arithmetic with arbitrary precision is also able to solve problem of ill conditions. So if you want to solve problems with the Hilbert matrix, you can try to prepare better method, or use arbitrary precision arithmetic, then problem will be solved. Full screen, is it full screen? Not. Now I want to make some numerical experiments for matrix inverse using different initial state matrix. We didn't make such experiments so far with matrix inverse. We use different values gamma, different time intervals. we worked with the matrix generated by generated by rand I command 3 times 3. We can expect that this matrix 3 times 3 square matrix is invertible because after random generation 3 times of 3 sequences, it is impossible to generate linearly dependent row. How do you know how to prepare matrix of ROM? R of dimensions 4 times 3 and rank 2. Do you have idea how to prepare 4 times 3 matrix of rank 2 or for beginning of rank 3? Full column rank matrix. Shabam, do you have idea how to generate? We will use random command. Four times 3 times it should be of rank 3. What is V0? Not defined. We used 0, I think. What is solution which we can expect? Here is solution which we can expect. Oops. A dagger plus V of 0 minus A dagger A V of 0. So V of 0 equals to 0 should result in Moore-Penrose inverse. Pin of A. Here is pin of A. I don't know how to increase. Here is minus 0, 0, 6, 1, minus 0, 6, 6, the same. 0.066104. 6.1, and finally difference here is 6.8. 6.8, the above is 6.1. So we can use model for matrix inversion to compute Moore-Penrose inverse of full row or full column rank matrix. But we must choose zero initial state. If initial state is not zero, I think we will not obtain Moore-Penrose. Then V0, for example, we can choose to be A transpose. We can expect the same result. This trace A transpose minus A dagger A transpose. It should be again A transpose. Try. Yes, result is the same. Change. V0 can be and I. Of order, we used order 4 times 3, here 3 times 4. What is pin of A? To see again. First element is the same, but second is not the same. What is with pin of A plus V0 minus A dagger A, pin of A times A times V0. Not. Dimensions n times n, V0 must be n times m. N times m, n times m. We choose matrix 4 times 3. A, 4 times 3, V0, 0. Okay. V0 is equal to rand integer of in interval by 10, for example, 3, 4, opposite. V0, 3 times 4. Start now. This matrix can be different than AV of t is of order m times m. Okay, fast convergence. Result. Compute pin of A, Mulpenrose, plus V0 minus A dagger A V0. And it is the same as result. Same in many decimal digits, 0, 0, 6, 6, 1, 0, 4, 6, 1, 4, 2, still good, 6, 8, 8, 7, 9, all is good. But if we generate rank diffusion matrix, I think ZNN, the GNN design will have problem. We can try how to define matrix 4 times 3 of rank 2. Have you idea now how to do this? Two-rand product of two-rand functions. We will use random integer for 3 times random integers. Am I behind this? 3 times 2. This matrix of rank 3. Another one is of rank 2. And rank can be less than 2, but suppose such situation is theory. Suppose we will try. For 3, first one, I will use this with copy, very small font. I have problems to see all. And del 3, 2. It is our matrix of rank 2. Now we should see the V0, return V0 to 0. Without V0 equals 0, we cannot expect results, definitely. V0 equals 0. What should be I identity matrix? I is now 4 times 2. V is 2 times 4. So AV is of dimensions 4 times 4. It is logical to expect I to be 4 times 4 dimensions. Try. Computed. What is pin of A? The same. We can try with non-zero matrix V0. Random. Which dimensions should be of V0 now? A is of order 4 times 2. V0 is of order 2 times 4. Try now. Here is confirmation that model for matrix inverse can be used to generate Moore-Penrose inverse with particular choice of matrix, of initial matrix. Here is a model for computing matrix inverse. Simulink is there. And we can try to compute Moore-Penrose inverse for some particular choices. Now you can try with this model. Who wants to try with this Simulink to change parameters, define matrix A, and or what is necessary? Who is so brave to try? No. Can you do this? No. Colleague, can you do this in common? Try. You can try this in common to do. Shabam, do you want to try? Nothing is dangerous here. I will show. I will be here. Here. Here is model. What we need to define? A, matrix A. Here is transpose. interval is from 0 to 10 minus 8. What is here? 0 initial state. We don't need to do anything. Is gamma defined? Constant -1 is okay. We need minus gamma. Ooh, very big. Very big. Gamma defined. Only we need to define matrix A. Yes. It is Simulink model. We need to define A in command line. Here is A equals, we can type a rectangular matrix can be, or can use rand. Rand is for generating integers. We can specify order. We can specify interval first. Here 1 to 10 is means give me random integers from this interval. We can change interval. We can not use interval, then interval will be 0, 1. And specify dimensions. Okay, comma, and then, okay, the arbitrary dimensions. Our matrix will be generated by random integer matrix from this interval, the integers. Okay, press enter. Generated, it is our matrix A. The matrix A is defined. Now we should test this. Here is run. Works. Goes. Go. Yes. Different color for each element. Looks finished. We can change color. Double click on time scope. File or view. We need property editor. File then. Print to figure. And there is file. Then we can use file save as. And then make fig file. This fig file will be available for changes. We can put this fig file on our hard disk and use later to change this figure without another running of MATLAB. Okay, we want to change properties. View. No. Okay, configuration properties. No, property editor. File, view, not view. File. Into figure. Is it figure or not? Here is figure. View now. Property editor. We didn't use fig file. Used generated in Simulink and have no property editor. In fig file we have property editor. Use bigger. And then down, then press to arbitrary element, down, change properties. Here is color, black to white. Okay, arbitrary color. Can we press on one graph and change properties of this graph? And in this way, we can change arbitrary. There is white black, white background. Can we use white press background and then change to white? And then change one by one. That's it. What? I will not save. In any case, it can be better. Yes, put many. We can put here is very, very small. It can be changed here to put arbitrary text. Font can be font size for this, for example. Or slower because of connection and works slower. Here is font size, Helvetica, font is Helvetica 8 to bigger, much bigger. Changed. Here is 24. We changed this font from 8 to 24. So we can change all details. We can put dots, can put rectangles, squares of our lines. Can. So convergence in beginning was not so easy, and finally very quickly found a right trajectory. It was zero initial state. We can change initial state. Initial state is in, I opened here all Simulink models. Now, can we close this? MP inverse. It is our model. Command line. In command line, we define all, make problems, programs as it was yesterday. What are appropriate dimensions for V0?
6 cross 5.
Opposite dimensions then for matrix A, because V0 must be compatible with Moore-Penrose in addition. And we should choose V0 in our case of dimensions 6 times 5. Right? It means global convergence. global convergence don't depends on initial state. Convergence is not global if we ask some specific conditions for V0. Here V0 used in random way. Of opposite dimensions than A and worked. Okay, now we will try with another model. It is not full screen, yes. Model for computing aimed to computing outer inverses and able to compute 2-4 inverses. We spoke about this model for outer inverses, but the final result was 2-4 inverses. We need one matrix of order m times n, another matrix G of order n times m, rank of R is S, rank of A is R. S should be between 1 and R. And condition rank of GA equals rank of G must be satisfied. This condition must be satisfied. Model corresponding to error function A V of t minus GA V of t minus G is defined as V dot of t equals minus gamma GA transpose GA V of t minus G. V of 0 equals to V0, arbitrary. V0 is arbitrary. What was expectable as final result? Final result is V tilde of V0 equals GA dagger G plus V0 minus GA dagger GA V of 0 I will close previous GNN models. Here is this GNN model. Zero initial state. G not defined. We need to define G. Need to define A. Gamma defined. It is block for matrix transposition. It is a two workspace block which will store values of V of t. We need one more, which will store Frobenius norm of error matrix. I will put this block here. Now works. Sim out is name of this block. Time interval is 0.5. Gamma is equal to 10 power 6. I will ask a smaller time interval, 0.1. Save this model because I included here one two workspace block. And now we can try. Who is willing to define A and G? And Can you? So I'm not one more. Do you want to do this? Okay, okay, thank you. We need command line. Here is command line. GNN ATS2 is our model. Here is command line where we must define A and G. We can choose a rectangular matrix. Which dimensions do you want for A? A equals, yes, random. Oh, you want to type? Okay, it can be better random. If we type, can be. Okay, we can finally type, no problem. Rand. It will be a matrix of real values. Okay. Rand I in the end will means integer. It is easier to trace. It will be real matrix, something, dots. It will be integer, easier to trace. Without I, will be matrix of real numbers. Then we have different parameters. First, we can specify interval. Two to 12, for example. What? Interval 2 to 12, we choose. And then dimensions. For example, 6 to 6 times 2 times 4. It will be from integers. 6 times 4 of rank 4. If we want a rank deficient matrix, we can use product as in previous case. If you want, we can use immediately. Okay, enter. Looks generated. Then generate matrix. We need to generate matrix G, integer, 4 times 6 matrix of rank 3, for example. Opposite dimensions, and we choose smaller rank than rank of A. How to do this? Rand I interval for 3 times interval 3 to be possible to multiply 3 and 3 here must be identical. 6. It should be. It should work. This one is 4 times 3 of rank 3. Another one is 3 times 6 of rank 3. And we can expect that product is also 3. Very small probability is that rank is less than 3. But if we type, then it is possible to be sometimes. Rank of GA should be equal to rank of G.
Sir, the only condition on G is rank of AG, it should be rank of GA and rank of G. So the choice of G does affect the computation, or any G can suffice?
Choice of G? What choice of G? Would you repeat, Srivan, please?
So in this, we are finding the 2, 4 inverse of the A, and we are choosing G, which
A and G, we must choose 2 matrices.
So
Both matrices must be included, and both matrices are beginning of Simulink. A is of order m times n and rank R. G is of opposite order, n times m, and rank S, which is between 1 and R, rank of A. 0 is bad choice, why to use 0. And rank of GA must be equal to rank of G.
So any choice of G, do we need a specific type of G, or any matrix G can
Any
suffice?
matrix G.
So it does not affect the computation.
Any matrix G with conditions which we specified earlier. Rank of G, G is of opposite dimensions. Rank of G is less than or equal to rank of R, and rank of GA must be equal to rank of G. 3 conditions.
So if we
Not so arbitrary, we cannot type whatever we want. First arbitrary dimensions, then rank arbitrary.
So if we induce some structure to G, can we imply the faster convergence or something?
Some specific structure. We can ask G to be a structured matrix, diagonal, three-diagonal, and so on. Results should be the same. Finally, this GNN model is not adopted to some specific structure of G. I had frequently questions about is it possible to prepare GNN, to prepare ZNN model according to specific structure of input matrix. So far, I didn't find such papers. It will be good to investigate, finally. Defined. Enter. Aha, 4 times 6. Rank of G, 3, as we want. Rank of GA, rank of G. Oh, we have time. A, also 3. All looks okay. Opposite dimensions, rank of 3. What is rank of A? Can we try? Rank of A should be 4. All looks according to rules which we have. And after that, we can try what? 4. Of course, we expected 4 from integer numbers of 6 times 4 order and rank 4. We expected it. Rank of G should be less than or equal to rank of A. And we choose case when rank of G is smaller than rank of A. Can we try with our Simulink? Here is in MATLAB. We spoke GNN ATS2. It is for inverse. We can close this. Don't want to save. MATLAB. Here is command line. Here is our model. Try and we will see what will happen. Run. Is green. Ooh, very quickly. Error is 0 times 10 minus 13. Really small error. We can believe it is good. Now we can plot what was gamma? I forgot. 10 power 6. In command line, we can plot sim out. It will be graph of Frobenius norm of error function. Plot of sim out. Bad name. We can change this. Very fast convergence. Probably it is near. Plus, we can use plus. And we should find where is beginning. We can try with some shorter time interval, 10 power minus 6, for example. Try now. Plot again. It is very fast convergence. We cannot find beginning. 10 minus 9, yes. Because of that was difficult to find beginning. Then minus. Here is, now it is visible. Fast convergence. But we found it in beginning of axis. better is to choose even shorter time interval, -8, and gamma much smaller than power 2, for example. Now we can try start and use plot again. We have no convergence visible. Plot line, we will ask plot line, the command line. We can use history here. Enter. Here is not convergence to 0. All is around 48 or something. It is far from 0. We didn't achieve convergence. Okay, we will save this. We can use it's different. I think it's all. We cannot do smaller. Okay, I want it to be smaller. Now we will press command hold on. It means save this graph. Save this graph. I will do something, and later I will put new graph on the same place. In this way, we will be able to compare influence of parameters. Understand? Now this graph will wait us. We want to increase gamma and compare smaller and bigger gamma. Go back to Simulink. Change gamma from 10 power 2 to 10 power 4, for example. Okay, and then run again. We must run to obtain the result. It looks better. Then command line, MATLAB, command line, plot sim out again. We can use history. Better is to use history. Run and enter. And enter immediately. Now, MATLAB and find our graphs. Can you see difference? Visible. Blue line better visible and red line below, which means new value of parameter gamma equal to 10 power 5 is better than previous value. We can use even smaller values of gamma.
Both graph, current one, earlier.
We can try more, but don't forget, hold on. If we forget hold on, all will be removed. Hold on command enables to save current graphs. Did you press hold on? We will use history. Much faster. Back to MATLAB. Here is Simulink, I think, visible. Click. Gamma, double click. 10 power 6, for example. Okay, and then run. Fine convergence. Now we have fine convergence. Back in MATLAB, command line. And then plot sim out again. No, no, no. History, history. We want to do the same. Enter. Now find our graphs. Here is, they cannot see this. You can see this. We can use plus. This orange is much better. It is new graph. Now you can see 3 graphs. Much better, better and better. And so on, if we continue in this way, we clearly can see influence of gain parameter. Not so difficult. Okay, requires time, yes.
What is this?
This graph is graph of V of t. V of t. I spoke that many times. I had a question of type 1 V of t and many graphs. Of course, many graphs, because V of t is our approximation of matrix of outer inverse. Element-wise, element by element, each element. And each element goes to stable value after some time, goes to equilibria state. This stable value is called equilibria stage. Okay, thank you. What is V of 0? Shaban, can you help us more? Can we see what is V of 0? I forgot where to find V of 0. You can help me. V of 0. Double click. 0. So which result we can expect? 0, 0. We can expect GA can we see? Please compute GA Murpenrose G and compare with our result. What we obtained. Command line, and type pin of G star A star G and compare this result with result
Minus 0.0.
looks looks we obtained GA dagger G, but we can change V of 0. Please change V of 0 and compare result obtained that. What are the dimensions of V of 0? Where it is visible. The same as dimensions of GA dagger G. In general case, it is of dimensions 4 times 4 times 4. And then 4 times 6. So overall dimension of GA dagger G is 4 times 6. It should be dimension for V0, opposite than dimensions of A. Of course, because we found generalized inverse of A and dimensions of V0 must be opposite than dimensions of A. Huh? Did you define some command line? Press MATLAB. Here is mouse. Here. V0 equals A transpose. Opposite than dimensions of A. So we can choose A transpose. For example, it is only one choice. Of course, there is infinity many different A prime. Prime denotes transpose. Try now. The same, The same.
For A prime, it is giving this answer. It is getting answer.
We can increase this, no problem. Mhm. Mhm. Of course. It is the same as previous answer.
It was same as previous one. But if we take,
Can we verify? Huh?
we take random,
Mhm. Okay, we will verify. Are you sure it is the same? Huh? Another one.
2.027.
We use this, it will be visible then.
0.027. If we take E prime,
Try to compute GA dagger G plus V0 minus. Possible that A transpose is not best choice. Later we will use random matrix. Star V0. V0. Not V0 in first case also. V0. V0, capital V. Not VO. VO. V0 inside here. Capital V. Not capital. Is it the same? Can we see beginning? Press here and not V0 here. Click. And should be different.
it should be, it is different.
Yes, it should not be different. What was V0?
0 was A prime. If we
Mhm.
take random, then it is getting changed.
But not small V0, capital V0. So, capital V. Because of that, we didn't had effect. Not small V0. You told small V0 equals, we need capital V0. And we didn't change initial state and of course obtained the same as previous result. Capital V. A sense, capital V. It will work. Capital V, change. Case sensitive. Programming languages are mainly case sensitive. Again, the same. Evaluate.
Pick random.
Take random. Please take random. But opposite dimensions than matrix A. Opposite dimensions.
4, 6.
Or 6. Yes, it's true. Now. Give me vol.
Getting phone.
Looks the same. Yes, here is 0.
Should be easy.
V0. Here is fixed initial state 0. Now try different, because in integrator we had fixed 0. And we change V0 with no influence of this model. But we should put, we can compute. Of course it's true. Try full screen, this one here. Press. It is full screen. Typically goes in this way. Difficult to find. Can we, from command line, compare result with this one? From command line, yes. Find previously. Not small, capital V0. Yes. Looks.
0.06.
What was our mistake? We had fixed 0 in initial state and changed V0. We forgot that in our integrator is fixed 0 initial state. And when we put V0, which should be defined from command line, we obtained appropriate result. Only V0 equals 0 will give GA dagger G. Another V0 will give such result. It is important result to remember. We have 6 minutes more. I promised one job for you. Promised you will do something. How from this model will be possible to generate model without GA transpose? What we need to change? We don't need GA transpose. We need only this one. GAV minus G. We don't need this. Eliminate. Only delete. Only. It is more difficult. No. When I have such problems, I use delete. Delete connections, unnecessary connection. Matrix multiply. This red connection is, no, we don't need this. Delete. Don't need this, no. This matrix multiply is used to define -1 we need. No, don't need. Gamma need. This text don't need. We don't need this text. Requires work. It is how to say, experience. Requires experience when you spend many hours in MATLAB and in Simulink, you'll be better. For one day, you can work all the day, but you will not be experts. You can work 7 days, all day, you will not be expert. But if you work 1 hour, 1 year, you will be better. Did you prepare? We need this. With gamma, minus gamma. If it works, we succeed. We'll have nice weather outside. We will finish. Sure. Did you try to? Result will be different.
Should take 0
V0. V0. Put 0 in any case. Don't forget that eigenvalues must be positive. Eigenvalues all depends on eigenvalues. Command line change what are eigenvalues? I, A, no, only A. Small fault, something is wrong with my computer. There are negative values. Negative value. If we have negative eigenvalues, we cannot obtain result. use G equals A transpose. It will work, A transpose. Then we will have egg. What are egg? Positive. As bigger agent values, as better will work. Try now. Of course, bigger gamma, bigger time interval. Mhm. Thank you, Shabam. Safik, it is. Mhm.
Yeah, thank you very much, Professor Petra, for your nice tutorials. If you have any questions, please.
No questions
question?
after all.
Okay, then give big thanks.
Finally, it is tutorial. Okay.
So numbers are gradually decreasing. Okay. So many things we are discussing, and your PhD or also MSc students take some problem from here. Okay. So you won't get time. Huh? Even you search 1 year literature survey, you won't get any good problem. That is the big research